Hello everyone, you have a quiz number 2 coming up. So I want to give you brief review. Okay, so review quiz number 2, and quiz number 2 is from chapter 7, 8, 9, 10, 13 and 14. Okay, so simply you have to prepare work, energy and power. Okay, you have to study the rotational motion, you have to learn gravity, circular motion and projectile motion. Okay, and you have to learn fluid. Under chapter 13 and 14 you have to learn here density, pressure, buoyant force and Archimedes principle. Flotation, and you have Bernoulli's principle also. So roughly if you prepare these topics, I think you are good to go. Quiz number 2. Okay, so the chapter 7, I do not take a time. Chapter 7 is basically work, energy, power chapter. Okay, so you recall the definition of work. Your work done is W, which is F times D, basic formula, and another formula is W. This is equal to FD cosine theta. Okay, so if you know the force and if you know the displacement, like this, you have an object, and if the force is applied like this horizontally, and object is moving in the same direction, in this case simply apply the force. This force is a constant force, not a changing force. Applied force multiplied by displacement, that gives you the displacement. But sorry, that gives you the work done, not displacement. Applied force, it is constant force, and this is net force also. Okay, if there is a friction, then you have to subtract the friction force. So F times D, this is a net force and this is a constant force. And if the force and displacement they are parallel, you can use this formula. But if you have, this is horizontal plane, and let us suppose the force is in this direction, this is the force and this is the direction of displacement, this is the displacement. If this angle is theta, then in this case your work done is FD cosine theta. Whatever theta given here, plug the force here, displacement there, and theta, whatever theta given, plug the theta and multiply this, you get the work done, which is in joule. The unit of work done is joule. This is very simple. Okay, so if you do your homework carefully, you can do the quiz also. Okay, the another important thing here is energy. You know, we talk about potential energy, we talk about the kinetic energy. So we have a gravitational potential energy. Simply you can write down PE, the gravitational potential energy, This is equal to mg8. This is gravitational potential energy. And if you want to write down kinetic energy is 1/2 mv square. So if the object has a mass m moving at like v, then multiply mass and v square and divide by 2, or 1/2 mv square. This is your kinetic energy. So kinetic energy is the energy due to the motion, energy associated with motion. If the object is in motion, then you can calculate the kinetic energy. Potential energy, energy due to the position of an object. And to calculate the gravitational potential energy is mgh. So if this is a ground, from here you measure the height. So let's say x equal to, you can use y, not x, y equal to 0, or that means right here your h is also 0, height is 0. Now this object has a mass m. If you lift this object up here, right there, this height is h. If the height is h, then this object store the potential energy. We call this is the gravitational potential energy, and gravitational potential energy PE, this is equal to mgh, mass times gravity times h. Okay, so mass is given, gravity is 9.8 meter per second square downward direction, and height is 8, it is also given. Then you can easily calculate the gravitational potential energy. And there is another potential energy we call the elastic potential energy, that is PE elastic. Okay, so the formula is like potential energy, this is, you can write down 1/2 kx square. K is a spring constant, K, this is spring constant. Okay, and x is the change in length of the spring. Change in length of the spring. So if I give you any problem, I'll give you the K, I'll give you the x, then simply you can plug in this equation. So this is the elastic potential energy. So the only thing is you have to calculate the change in length of the spring. So simply if this is your spring, there is no change right now. Now if you attach the mass right here, what happens? The spring is elongated then, like this. Now from here to there, this is your x, this is your change in length. Just you have to calculate this and plug here, you can get the elastic potential energy. So this is not a big deal. And the important thing here is conservation of energy and conservation of mechanical energy. Please watch the video carefully, okay? Conservation of energy is neither created nor destroyed, but you can transform from one form to another form. Energy you never destroy, you never create, but you can transform. The electrical energy can be converted into heat energy. The electrical energy can be converted into light energy. Light energy can be converted into electrical energy. You can convert, you can transform from one form to another form, but you cannot destroy. That is conservation of energy. But there is another one, conservation of mechanical energy. Conservation of mechanical energy, that is, look here. Let us suppose this is the ground. You have an object here. This object has a mass m equal to, let's say, 10 kg. And this object is at a height, let's say, 10 meter. Height is 10 meter. If you release the object from here, you drop the object from here, what is the kinetic energy before hitting the ground? Before hitting the ground means very, very close to the ground, because after hitting it comes to rest. Heat energy produced, that is different story. Okay, so before hitting the ground, like right here, what is the kinetic energy here? So the idea is conservation of mechanical energy. If we ignore the air resistance, the sum of the kinetic energy and potential energy remains constant. For example, if you call this is point A and this is point B, the idea is kinetic energy plus potential energy at point A, this is equal to kinetic energy plus potential energy at point B. That means, look here I release the object, initial velocity is 0, that means initial kinetic energy is 0, so this energy is 0. Potential energy mgh, this is equal to, now at point B we consider height is 0 because it is very, very close to the ground. Height is 0. If height is 0, your potential energy is 0. But the kinetic energy is 1/2 mv square. So you can write down mgh equal to 1/2 mv square. So now look here, mass is given, gravity is 9.8 meter per second square, height is also given 10 meter. Plug here like 10 kg, 9.8 meter per second square, and 10 meter. So this is 1/2 mv square. This is the kinetic energy. Now whatever you get, how much is this? Is it 980? I think 980 joule. This is your kinetic energy, 1/2 mv square. Kinetic energy. But sometimes people, they can ask you, what is the speed then? What is the speed before hitting the ground? You can calculate from here. Look, I already did it. 1/2 mv square. This is equal to 980 joule. So if you need the speed, what you can do is, you can do this mv square equal to 2 times 980, because I multiply by 2 here, I multiply by 2 here, so these two cancel out, and divide by m here, divide by m there. So v square equal to 2 times 980 divided by m, and v is square root 2 times 980 joule divided by m is, it is 10 kg. 10 kg. So whatever you get, please use your calculator, you get the speed, meter per second. Okay. So this is about the conservation of mechanical energy. Please watch the video also, that is also helpful. So you need to know this. Okay. Another motion is, like another chapter is rotational motion. Under rotational motion, I cannot explain everything else here. Okay. You need to know what is frequency, what is the time period, what is like angular momentum, what is linear velocity, what is angular velocity, what is merry-go-round, that kind of things. Okay, so the linear velocity, simply linear velocity is x divided by t. Angular velocity, if you are running in if you are rotating like a merry-go-round, you have an angular velocity. Angular velocity is it is simply denoted by omega. Okay, angular velocity is omega, and there is a relationship between linear, this is your linear velocity. Linear velocity is v, angular velocity is omega, this is delta theta divided by t. This is radian per second, this is meter per second. So there is a relationship between linear velocity and angular velocity. Okay, the relationship is linear velocity is r times omega. R is the radius of the you have a circular path there. Like let us suppose something is rotating like this. Let us suppose something is rotating in a circular path like this, rotating like this. This is the r. Okay, radius, and here you have a linear velocity v. If the linear velocity is given, radius is given. This radius is given, linear velocity is given. How do you calculate the angular velocity? Use this relationship. Whatever given, if v is given, r is given, you can calculate the angular velocity. Angular velocity is, you can do this, omega equal to v divided by r. Or if the angular velocity is given and radius is given, if omega is given and r is given, you can calculate the linear velocity also. For example, if the let us suppose omega is 5 radian per second, for example, and if the radius is 2 meter, what is your v then? What is v? Just plug here. Your v is, r is 2 meter, omega is 5 radian per second. Okay, so this is 2 times 5, 10 meter per second. That's it, 10 meter per second. So please write down this formula, v equal to r omega, you need this. Okay, then you can think about the merry-go-round also. You can think about the merry-go-round. Merry-go-round is something like this. You have a pole here, and there is a beam, and it is rotating this direction, counterclockwise. Let us suppose you have a horse A here, horse B there, horse C here, and horse D there. One child is here, another child there, another child here, another child there. I just draw the chair there in place of horse, okay, that's the same thing, okay. So now it is like this. You can think like, I don't know if you see this, here you have one horse is there, another horse is here, another horse is here, another horse is there, okay, and the A is here. So it is something like this, okay. Look, A, B, C, D, 4 horses there, and kids are there, okay, and it is rotating like this. It is rotating like this. You understand me? It is rotating this way. Now the question here is, you have A, B, C, D. Who has the maximum angular velocity? Who has the maximum angular velocity? Or do they have the same angular velocity? What do you think? Think a little bit. A, B, C, D, who has the maximum angular velocity, or do they have an equal angular velocity? What do you think? Angular velocity omega is equal to delta theta. This is angular displacement divided by time. This is the angle made by each kid. So look at this. So look at this. Right now the angle is 0. If you rotate this way, everybody they make the same angle, equal angle. At the same time, everyone they make same angle. And look, angle divided by time. Time is same, angle is same. What about the angular velocity then? Everyone they have a same angular velocity. Everyone, every kid has same, equal angular velocity. Angular velocity. But what about the angular velocity is omega, okay? Angular velocity. But what about the linear velocity? Linear velocity is V equal to R omega. Omega is same for all. Omega is same for all. But R is different. Look, this is R for A. This is R for A. This is R for B. This is for B. This is for A. This is R for C. So you can write down RC. And this one, this is R for D. Now look at this. The radius for D is maximum. This D R is maximum for D. Omega is same for all, but R for this kid, D is big. Now if you multiply the biggest number and omega, of course D has the maximum linear velocity then. He has the smallest linear velocity. Please recall this. This is the merry-go-round thing. And you can also think about the angular momentum and moment of inertia, rotational inertia. Please recall rotational inertia. It is simply denoted by I, and angular momentum. Angular momentum L. Angular momentum L is equal to I times omega. I is the rotational inertia, omega is the angular velocity. Rotational inertia is inability of an object to change the state of rotational motion. Okay, that is called as the rotational inertia. And simply if the object is really tiny, you can write down I equal to mr. So like this. You have a tiny object. This is a tiny object rotating about this axis. This is R, mass is m. This is a tiny object, okay, really tiny object. So in this case, I is mr square. But different objects they have a different formula, okay. But if it is a tiny point size object, then simply in that case we can write down mr square. So angular momentum is rotational inertia times angular velocity. So again, I have to recommend you to watch the pre-recorded YouTube video, but here I can talk a little bit about the conceptual questions. So like the ice skating things like the dancing dolls, like she is spinning really really fast, and if let us suppose the girl is dancing and her arms are closed and she is spinning really very fast because the floor is frictionless. Now she has to slow down. What she has to do to slow down is she slowly stretches her arms like this. I think I showed you the demo in my video also. Or if this is not enough, you can spread your leg also. Then she slow down. In this case, if you stretch your arms like this, your angular velocity decrease, moment of inertia increase. Now think other way. Let us suppose you are spinning like this way. Now if you slowly bring your arms closer, you spin fast. That means your angular velocity increase. You spinning fast, angular velocity increase. If your angular velocity increase, your rotational inertia decrease. Okay, this is one example. Another example, you can think about like, let us suppose, this is interesting everyone. Let us suppose this is earth, and this is axis, and there is ice. This is ice, okay, and earth is rotating. Earth has two types of motion. One is rotational motion, rotating, spinning. Another one is circular motion. So time taken to complete one rotation, one spin, that is time period for rotational motion. Time taken to complete one revolution, that is also time period for the circular motion. For the circular motion, the time period of the earth is 1 year, 365 days to go around the, I think, sun, right? So time taken to complete one circular path, one revolution, that is called as the time period for the circular motion. For example, if any object, not earth, any object make 2 revolutions, let's say 2 revolutions in like 4 seconds. So what is the frequency then? You have to calculate the time period. Okay, 2 revolutions in 4 seconds. What is the frequency? Because the frequency is 1 over time period. 1 over time period. If you make 2 revolutions in 4 seconds, what is your time period? Time period is only for one revolution. So if you make 2 revolutions in 4 seconds, you make 1 revolution in 2 seconds. So the time period is 2 seconds. So what is the frequency then? Then frequency is 1 over time period. That means 2 revolutions in 4 seconds. That means 1 revolution in 2 seconds. So time period is 2. So your frequency is 1 over 2 hertz. This is how you have to calculate the frequency of the circular motion. But here I am talking about the earth rotational motion. Earth spin about its axis, and earth time period is 24 hours. That is 1 day. 24 hours is 1 day. Okay, spinning rotational motion. And there is ice. Let us suppose this ice melt. Ice melt and it becomes water, and water come over there distributed here. Here. It is like this. Think, I do not have a demo for this. Think, I am the earth. Okay, my hand, this is the ice right here. Pole. Okay, here. Ice melt. If ice melt, and you know that earth is rotating like this. Earth is rotating like this, and time taken to complete one rotation, that is 1 day. So in this position, ice is here, and the length of the day is 24 hours. Now ice melt and come to the equator. That means it is like this. What happened to the motion of the earth? In this case, earth rotates slowly. Now what happened to the time period, rotational motion? Increase or decrease? Increase. Time period increase. What does that mean? More than 24 hours. So your day becomes longer. If the ice melt, this ice on the pole right here, if this ice melt, ice go to the equator side like this. Here, consider my hand is ice, and ice melt. It distributed like this. So rotate slowly. That means it takes a long time to complete one spin. That is 1 day. So the length becomes longer. So please recall that kind of thing. That is helpful also. So, and this is about the rotational motion. But you know, even ice melt, it spins slowly or it spins fast. If there is no external torque, angular momentum remains constant because you have a conservation of angular momentum. In the absence of an external torque, the total angular momentum remains constant. Please recall that. Okay, so this is about the rotational motion. Then we have another one like a gravity and circular motion. Gravity is really straightforward. If you have two objects, one object is m1, another object is m2, there is a force between them. Okay, the distance between them is d, so the gravitational force between them is g m1 m2 divided by d square. Okay, and if there is a gravitational force, look, one object here, another object there, there is a gravitational force, and if they are moving closer, what happened to the acceleration then? Increase, decrease, remain same. The acceleration of each object, because if the object is coming closer, force increase. If the force increase, you know the formula also, the Newton's second law, F equal to mass times acceleration. So A equal to F over m. Okay, if the object comes closer, your acceleration increase. Please think about this. And this is about the gravitational force. There is more, please watch the YouTube video. And there is a circular motion if the object is moving in a circular path like this. Let us suppose this is a circular path having radius r. Object is moving in a circular path, mass is m, moving in a circular path. Let us suppose this is the speed. If the object is moving in a circular path, to keep the object in a circular path, you need a force. That force is called as the centripetal force. To keep the object in a circular path, you need a force. Because in a circular motion, uniform circular motion, there are two types, uniform circular motion, non-uniform circular motion. Uniform circular motion also needs the force to change the direction because object is moving in a circular path. And that force is called as the centripetal force, and the centripetal force is always pointing toward the center of the circular path. So to keep the object in a circular path, you need a centripetal force, and the centripetal force is always pointing toward the center. And if the object is moving in a circular path, the direction is continuously changing there. That means the object is accelerating, and that acceleration is pointing toward the center of the circular path. And that acceleration is called as the centripetal acceleration. Centripetal acceleration AC is equal to v square divided by r. AC is equal to v square divided by r, and centripetal force F of c equal to mv square divided by r. So to keep the object in a circular path, you need a centripetal force. And if there is a centripetal force, of course, then you have a centripetal acceleration. Both centripetal acceleration and centripetal force, they are pointing toward the center of the circular path. Okay, and time taken to complete one circle, that is called as the time period. And 1 divided by time period, that is frequency or number of revolution, how many revolution you can make in 1 second, that is called as the frequency. Okay, so this is the main point about the circular motion, centripetal force. Okay, and another type of motion is projectile motion. Projectile motion. If you throw the object, in the space, in the air, and if the object is moving under the effect of gravity only, that is a projectile motion. Okay, object moving under the effect of gravity only, that is a projectile motion. Projectile motion has a two component, horizontal component and the vertical component. Horizontal component is constant because there is no force. Vertical component is changing because there is a gravity, downward direction. So object is accelerating downward direction, but horizontal direction, it is constant. Now if you throw the object like this, by making certain angle, like a 45 degree angle, like a 30 degree angle, if you throw the object like this, okay, do you see, I said this, if you throw the object like this, what happened to the gravity and acceleration due to gravity? No change. Go up, coming down, g is 9.8 meter per second, so you are always vertically downward. But what about the horizontal motion? Horizontal motion is also constant. What is changing then? Your vertical component of the velocity. If you are going up, your vertical velocity is decreasing. Right here it is the maximum height. Right here the vertical velocity is 0. And when you coming down, your vertical velocity is increasing but downward direction. Only the vertical component change. If you are going up, your velocity decreasing. I am talking about only the vertical component. Okay, the vertical component of the velocity is decreasing. At the point at maximum height, your vertical component of the velocity is 0, not acceleration. Only the vertical component of the velocity is 0. And coming down, your vertical component of the velocity is increasing but downward direction, negative direction. That's one thing. And another thing is, let us suppose this is your horizontal line, and if you kick the object from here, let us suppose this velocity is 15 meter per second. Let me call this is v0. Okay, and this angle is theta. Theta equal to 25 degrees, or whatever angle is given. You need a calculator. Okay, and what happened? This object is, it goes there, and from here to there, this is called as the delta x. Okay, and this is called as the maximum height h. Now the question here is, what is delta x here? We call the horizontal range. This is called as the maximum height, and time to go from here to there, that is called as the time of flight. But my concern here is, what is delta x? Look, this is your v0. This is your v0. It has a two component. One component is v0x, which is v0 cosine theta. Okay, and another component is here. This is your v0y. v0y is v0 sine theta. Okay, now to calculate this delta x, you can do this. Delta x divided by t equal t. Let me use total time of flight. This is equal to v0x, or simply delta x equal to v0x times t. So if you know the horizontal component of the velocity, which is constant, v0x or vx, that's the same. Okay, v0x, and this is a time, total time. We call time of flight. So calculate the v0x, and if the time is known, you can calculate this. But here we have a direct formula also. I can give you the direct formula. So to calculate this delta x, in this case particularly, only in this case, okay, in this case you can write down v0 square sine 2 theta divided by gravity. This is the formula to calculate the delta x in this case particularly. There is another case also, I'll talk about that. So in this case you can use this formula directly. Okay, so here v0 is 15 meters per second square sine, what is sine? 2 theta. Theta is 25, so 2 theta is 50. 2 times 25 is 50 degree. Divide this by 9.8 meter per second. So whatever you get, that is your answer in meter. Answer is in meter. Another example is, if you look at this, let us suppose this is ground, this is tower, this is a tower. You throw the object from here. Let us suppose horizontal velocity v0x equal to, let's say, 5 meter per second. Okay, and the ball goes like this, So what is this? This is also delta x. What is this? Delta x. So what you have to do here is, your delta x, this is equal to v0x times t. Okay, you have to figure out the time. Okay, if the height is given, if this height is given, use this, h equal to 1/2 gt square. You can use lowercase t or uppercase t, that is not a different thing. Okay, you can use t. Okay, using this formula, calculate the t, v0x is given, plug here, you can get the delta x. Okay, so that is another possible question. Okay, and then let us suppose there is a rescue plane. This is a rescue plane, and this plane carries the package like this, and it is moving at a constant velocity, moving in a horizontal direction, constant velocity. It carries the package. The victims are here. Okay, the pilot has to drop this package so that these people can grab that package. And I give you the option. Let us suppose point A, point B is vertically above the victims, and point C. This plane is moving at constant velocity, and the pilot here has to drop that package. From which point, A, B, or C, does this pilot have dropped the package? From point A, from point B, from point C? Think about it. Is your answer correct? The correct answer is the pilot has to drop the package from point B, because if the plane is moving like 400 miles per hour, the package also share the same speed, 400 miles per hour. So if the plane is moving, package is also moving. So if he drop the package from this point, what happens is package goes like this, and the victims, they can grab the package. Okay, victims, they grab the package. Pilot drop the package from point A, victim grab the package. Right that time, where is the plane? Package reach this point. Where is the plane at that time? Exactly at that time is right here at point B, vertically above the victims. Because the horizontal motion is constant, I said the plane is moving at constant velocity. That is why the horizontal displacement traveled by the package and the horizontal displacement traveled by the plane is same. So when the victims grab the package, at that time, exactly at that time, the plane is at point B, vertically above the victims. So please read the textbook, or you can watch the video also there. So this is about the projectile motion. And you also have to learn like a fluid, you know, you start from the density. Density is simply represented by rho, which is mass divided by volume. This is kg meter cube density, and you have a formula, pressure P equal to force divided by area. This is a pressure, force per unit area, that is called as the pressure. For example, if you have a tower like this, and if there is a outlet here like this, and you fill with water, and let us suppose water coming out from here with this velocity. Let me call V1. This is V2. This is V3. So which is greater, V1, V2, V3? The speed of water from here, from there, and from here. Which is big? Of course, this V1 is biggest. At the bottom one, this is the biggest one. Okay, because the pressure depends on height. There is another formula. Pressure is equal to rho GA. Okay, so the depth is in, look here, from this point above this, you have a huge amount of water. It doesn't depend on amount, but it depends on height. Okay, you have to think that way. So it depends on height. Okay, so this speed is big. That's the one thing you need to know, the pressure due to the liquid column. And another thing is you need to know the buoyant force. What is buoyant force? Buoyant force is upward force. Buoyant force, if you have an object, there is a liquid, okay, this is a liquid, and if the object is right there, for example, suppose, is this object experience any buoyant force? This object experience any buoyant force? Yes. If the object is inside the water, it experiences the buoyant force. Why? So there is a pressure here, let me call P2, and there is another pressure here, this is your P1. Why the buoyant force is there? Because P1 and P2, they are different. P2, this is the pressure against the bottom here of the object. P2 is greater than P1. P2 is greater than P1 because the reason of buoyant force is pressure difference. If there is no pressure difference, no buoyant force. But here the pressure against the bottom of this object is greater than the pressure against the top of this object. That's why the buoyant force is upward direction. The reason of buoyant force is the pressure difference. The pressure against the bottom of this object is greater than the pressure against the top of this object. That is why the buoyant force is upward direction. buoyant force. And the buoyant force is also, you know that, please again read the YouTube video. If you weigh the object, like if you take this object, in the and weigh it in the air, let us suppose it is 1 kg in the air, that is roughly 10 Newton. In the air it is 10 Newton. Now keep it inside the water. Let us suppose it is only let's say 7 Newton, I don't know, okay, only 7 Newton for example. So this object lost the weight. In the air 10 Newton, in the water 7 Newton. What happened to the 3 Newton? The 3 Newton is the buoyant force, upward force. Okay, that is due to the pressure difference. Okay, so weight lost in the water. Weight lost in the water is equal to the buoyant force. If you keep the object inside the water, it loses the weight. So weight lost in the water is equal to the buoyant force. That is one thing. And another thing is, like, let us suppose, think about the flotation. Let us suppose this is a pond. Okay, pond. And you have a boat here. This is a boat. The blue one is a boat. Okay. And you are here. To float, to float, you know, you must, including the boat weight, your weight, you have to displace the water equal to the weight of your weight plus boat weight, because you are on the boat. Okay. So if your weight, let us suppose, forget about the boat, let us suppose your weight is 700 Newton. You want to float. How much water you have to displace? 700 Newton. Because 700 Newton force is upward direction. Your weight 700 Newton is downward direction. So they cancel out. So if your weight is 700 Newton, you have to displace the water equal to 700 Newton. Displace water. Then you can float. That is a flotation. Let me give you another example. Let us suppose this is the level of the water right now. This point right here, level of the water. Consider this is the wood. Partially inside the water. And I have another wood. Both are wood, like this. The little one is on the top of the first one. Both they are floating. They are partially inside the water, but we call they are floating. And the water level is this. You see the water level. Now what I will do is, I take this off and put in the water, like this. And this is wood and it is also floating. It does not sink. I take off from the top of the big one, like this, and I put here. This little one is also floating, the big one is also, both are floating, but they are separate right now. Before it was like this. In this position, the level of the water is here. You can see the blue mark. This is the level of the water. Second position, the little object is here, but this is still floating. What happened to the water level? Right, this level, it goes up or goes down or remains same. What happened? Because to float, object has to displace the water equal to its weight. So in each case, they float. So they displace the water equal to their weight. So water level, it doesn't change, remains same, no change. Okay, so please read this, like it is buoyant force, Archimedes principle things, and there is like a Pascal's principle, there is a Bernoulli's principle also. The Bernoulli's principle is, if you have a high speed, low pressure, low speed, high pressure, that kind of things. Please read that. I don't want to make a long video, it takes a long time to upload. Okay, so I think this is roughly the thing you need to know to get the better grade in the quiz number 2. Okay, thank you.